Online people, good. I will try to have a change from my normal behaviour a bit quick. So, a lot of interest recently because of asteroidal satellites uh, and the raft of issues around there. A lot of people think it's straightforward stuff. It's obviously a satellite. Any double dip curve, people sometimes think it must be a satellite. We now have enough discoveries of asteroidal satellites to get a feeling for what the issues are. So we'll go fairly quickly, I hope, what the raft of issues are, and I'm going to quickly go through each of our ones and just point out what they were. And I'm going to do this in less than half an hour. Go. Big spy time occasionally. Okay. Multi-drop light curves can be a challenge. People, particularly in recent times, oh, double drops, I've discovered a satellite, woohoo. And then they get told, no, you haven't, or maybe you haven't. And negative reactions can come up really quickly. The change from excitement to disappointment. One of the challenges with asteroidal satellites, there is no simple test to say this is definitely a satellite. There are three possible causes of double dip light curves, which I'll go through. To say it's a satellite, you've got to exclude the other two. Oh, four causes.
One false.
Never mind. But the process of saying this is a satellite is a process of excluding all other alternative explanations. Now, when we get to a situation where satellite discoveries are more common than double star discoveries, then that might flip. And we could get to a situation where double stars are as common as satellites, then there may be some challenges there. So, possible explanations of a double dip light curve is a double star. A graze occultation, I've got the shape of Eros and Cleopatra. Depending on where the star goes past, you can see how you get a drop there and a drop there, or here and here. Double drop curves are usually associated with elongate asteroids. And then you have a satellite where each component of an asteroid is called a single star. Now, double star events and satellite events involve a common feature. It's one object interacting with two objects. In the case of double star, asteroid interacting with two stars. Satellite, it's two asteroid bodies acting with a single star. So there's that similarity in the two. They're just inverse relationships. Starting off with double star considerations, because that's the most critical distinction to be made. The distinguishing features is the magnitude drops will generally be different, but not always. And yes, and there's all sorts of qualifications about that we'll come on to. Importantly, both drops will be less than the predicted full drop, but that only is relevant if you've got a recording where the limiting magnitude is faint enough. The sum of the two drops will equal the expected drop, the expected full light drop. All this is ignoring the issue of Fresnel diffraction, by the way. Our light curves that we measure, they're generally uncalibrated. We just do an aperture, a background subtraction, subtract one from the other. And when people think, oh, the zero light level on there is a true zero. Well, if you're lucky, it is. If you're reasonably lucky, it's approximately about right. If you're unlucky, it's nowhere near zero. And of course, if you think it's a zero light level, how many times have you had light levels which are negative. When you see negative light, then you know that things aren't quite what you believe. So you cannot assume the zero level is the background subtraction. Because we're dealing with needing to have precise determination, you must have comparison stars, and you need to have a comparison star down at the low light levels. You need a comparison star that's a good 1 magnitude fainter than the target star. Which means if you're taking recordings where the target star is really just marginally visible, you'll lock yourself out of discovering a satellite. You need to be able to identify stars on the recording which are at least 1 magnitude fainter, 1 point more, preferably more. In terms of, well, one of the other issues is the camera spectral response. And if you have a V, this is a V magnitude and a Y magnitude. And if your peak camera response is, say, here, if your target star has got a colour magnitude slope like that, and your comparison star, so that would be a blue star, and this would be a red star. And if magnitude difference there is not great, magnitude drop there is large. If your camera peak response is in the middle, then the actual change there is less than what you think there. So you've got to be careful about when you're looking at comparison stars to try to have comparison stars which are of a similar colour to your target star. So the difference in the V magnitudes and the difference in the R magnitudes should be reasonably the same. If they're greatly different, then your comparison star that you're going to use for magnitude drops is not reliable. Okay, trying to keep this quick. You've got to be careful well, you need to be careful to include the asteroid's magnitude contribution in the light curve. So far, all of our satellite events, the asteroid's been quite faint, so you haven't had to worry about it. If you're dealing with a magnitude drop of just 1.0 mags, or certain less than that, then you've got to, the asteroid magnitude becomes a significant component of the light. And then you've got to be concerned about what is the real magnitude of the asteroid, because you have rotational variation in the light, which can be quite a few tenths of a magnitude. And that can have effect on your estimate of the magnitude drops. So if you've got a small magnitude drop event, the issue of the rotational light curve of the asteroid will make it fairly difficult for you to conclude, well, it creates problems in concluding that the light drop is as much as you believe it is, based on, because you don't really know what the magnitude of the asteroid is, and your ability to assess the appropriateness of the magnitude drop is reduced. That's probably not this. I haven't explained that really clearly. Main thing is if you're dealing with small magnitude drop events, don't think highly. The possibility of discovering a satellite is reduced. Small mag drop events, they're nice to say, oh, I got a 0.1 magnitude drop event, generally, the value in terms of what you get out of it is pretty minimal.
I suppose the reality is we're doing totally uncalibrated photometry.
Yeah, it's totally uncalibrated.
Probably any of the magnitudes.
Yeah. So all of that, there's stuff there. The rotation light curves can be quite different. Look, it varies in the orbit around the sky. There's no real ephemeris, really available ephemeris. So small magnitude drops, avoid them for satellites. Third, form on double star considerations. What happens when you've got a double asteroid occulting a double star? And we do have one instance of that. It's an occultation by Antiope, about 1910 or 1913, where the star was discovered to be double in the occultation. And you've got occultations by Antiope and I think two satellites. I think it was Antiope. It's got two satellites. And the report had got two sets of files with the complications of trying to sort out the double star effects and double asteroid effects. Now, if we were to get one of those in terms of an unknown double asteroid and an unknown double star, I have no idea how we'll handle it, or even if we'll recognise it. It's an interesting conundrum of what's going to occur. Now, the next thing is Fresnel diffraction. If the asteroidal satellite is small, Fresnel diffraction comes into play, and you don't get a full light drop. You only get a partial light drop depending on how small the asteroid is. I've got some very nice examples of this. But that if you've got a large asteroid with a small satellite, you can get a large drop with the main asteroid and a small drop. And you think, well, that's got to be a double star because the drops aren't the same. Well, no, that's not necessarily the case. And I've got some examples of that. And then if that last one, if in the right circumstances, and as we get smaller and smaller, significant Fresnel diffraction on both components, you get only partial light drops of both, giving the appearance of a double star. And there you've got to start looking at, well, from the light curves, what do I think the diameters might be? And you've probably got a iterative process to go through to try to figure out what the diameters are, which will match the light curves, and to see whether, in fact, it's a satellite or a double star, or you can't decide. But I've got an example of some of this Fresnel diffraction issues. Graze considerations. Graze events, you need generally elongate asteroid, or at least an asteroid which is large enough to have one side which is flat and appropriately oriented along the path of the asteroid's path. Statistics of having the asteroid aligned suitably and having the right bumps at the right place is probably fairly low, but they do occur. Now, you saw the pictures of Eros and Cleopatra earlier on, where you got clear bumps, or Eros, the bean-shaped thing. Long straight edge. I've got an example of that in what I'm going to show. When you're looking at an event with shape models, in the occult you can see shape models, a heap of asteroids. The shape models give you a general idea, but most shape models, well, the mathematics behind the shape models is very complex, And most models are done on the basis of all surfaces being convex. There's only a few asteroids, let's say, include concave parts on it. So that means that a model, most shape models, will not show depressions. So you might have what appears to be a fairly straight part on the shape model, and that could be an artifice of the shape model derivation. And you got to laugh the fact, well, that straight bit might in fact be a drop. And I've got an example of that. Generally speaking, well, expressly speaking, the two light drops have to be within the dimensions of the asteroid. The asteroid is this size and you'll drop here or drop over there. It's not a graze. If you've got an asteroid that size and drops there, chances are it's a graze. And if you don't have a shape model, what other information can you get that's relevant to deciding whether you've got an asteroid which could give a graze? And that's where you go to asteroid rotational light curve data. And there's various sources where you can get light curves, preliminary light curves. I won't go through the details. There's various sources to look at for light curve amplitudes, maximum amplitudes, where you can derive a maximum axis ratio. If you've got significant light variation in a light curve, that implies it's an elongate asteroid, which says, a graze may well be possible. If you only have a small light variation, that suggests that the asteroid is round, more or less, and that means the likelihood of a graze is pretty much zero. So if you don't have a shape model, then is it possibly a graze or not? You need to look at the asteroid rotation light curves, see if there's anything there that can assist with the guidance. And both events should fall within the length of the long axis. Here's the magnitude variation of the light curve and the axis ratio, like the minor axis to major axis ratio of the asteroid. So if you've got a 1.0 magnitude variation, peak to peak magnitude variation in the light curve, that suggests that the asteroid's got a length to width ratio of 2.5 to 1, which means graze possibility very high. And of course, you don't know the orientation of that, it's just a straight light curve. And I'll emphasize, to claim a satellite, you've got to exclude other explanations, and you can get a situation where you can't exclude that, so you can't claim it as a satellite. If you go through all that, and you've excluded all those, in subject to what Michael was going to tell us about the fourth explanation, which he can now come up with. What's your fourth explanation?
UFOs.
Oh, God.
Well, possibly identified.
No.
Now, if we're going to go to the frivolous...
Seriously, unidentified flight object, a satellite going through the background aperture of your star, raising the background, causing a doubling.
Michael does raise an interesting issue in terms of measuring light curves. One of the recent examples we had a single frame drop, looked really good. And it was measured with Tangra, so we got hold of the L.LC file, we set through it, and on the frame where the drop occurred, the measurement aperture had moved off the star.
Mm.
So the light curve appeared to show something, but it was an artifice of the measurement. And that is something anything with single frame drops, they're a nightmare to resolve, and you really need to look at the video. You can have cosmic ray effects on it. There's a single frame things are a problem. Really like to have at least 2 frames of drop light to be confident.
So you really do need the light curve file.
With all of these satellites, we insist on a light curve file, and we now have the arrangement with the Central Bureau for Astronomical Telegrams of the light curves are made available together with the CBAT announcement. So basic position is if you think you've discovered a satellite, don't argue about whether or not you want to provide a light curve. No light curve and it goes nowhere.
So I meant the actual Tangra light curve file of the video.
We can be asking for that, or there are times we've asked for the original AVI 5. Depends on circumstances as to how far you need to go back in terms of what you presented. But there have been some instances we've gone back to the raw video and explored that in detail. Other instances, it's so obvious you got heaps of observations at a point and it's clear video, you don't need to really go back to it. Other possibilities have been thrown up over the years of birds and planes and anything that flies through the air, including UFOs. Most of those, I mean, you start doing the mathematics of a plane, it's not going to be in the field of view for very long. But if you've got the central body of an A380 plane going over, and you happen to be perfectly aligned with your 20 centimetre cone going up there at that exact time, it could be a possibility. But those things, for the original things like Dave Herald's Arecibo, we had a serious battle. I say battle rather than fight, to deal with a couple of people who were arguing it might have been a plane or it might have been a bird, that type of thing, because there was a reluctance to accept it was a satellite. And that's tied in with what happened in the 1980s when there were a range of satellite claims on the occultation side, which were never substantiated, even though they got Hubble time on it and large telescope times, and they were never confirmed. And that's a history that we've had to deal with. And now that we've got them being common, that history is in the past. So, real life situations, I'm going to step through all the CBET events and just briefly talk about what the issue was with them. So you get a handle of it. There's 1 or 2 at the end which are pending events. So Arecibo, there's the light curves. Dave Galt and Peter Nollsworthy are about 20 kilometres apart.
Yeah.
In Western Sydney.
Mountains, really good check.
Yep. They got, both of them got occultation events. Interestingly, that chord, the top chord, shorter than that one for that event, but longer than the, the shorter and longer were different between the 2.
Mm-hmm.
Now, with that event, you could take that ellipse you fitted there and you could fit it to those events there. It could be fitted to it, which means the double, just on those chords, the double star option is live. But when you do the looking at these light drops, with comparison stars involved in it, those light drops were about 3 magnitudes or something. For an equal magnitude star, the light drop is 0.75 magnitudes. And throw in variation and so forth. We work on a basis you need to have a full one magnitude drop. But the drops were sufficient to I'd say that this had to be an asteroid. And of course, it was subsequent observation picked it up. This particular one has got to the stage where the Gaia people have, well, initially we asked the Gaia people, is there any evidence of this in their data? And they spent some time on it, and yes, here it is. And that led to the Gaia Moons project. Subsequently, they've done more research on that. We've got more occultations of it. We now have a full orbit of it, a characterization of the composition of the components. It's fully characterized, and in principle, it should be formally recognised with Dave Herald and Peter Nosworthy having naming privileges. But there's issues. The attitude with the relevant people is they'll only give a proper designation if it has been seen.
We answer things.
Yes, I won't go into there.
You don't have time.
No. This one, I mean, Dave got and Peter Nosworthy, I mean, they're satellite kings. The next one, they both had a single chord observation of a small asteroid. But when we plotted their observations out, I think that's Dave Galt and that's Peter Nosworthy. There's their two chords. That represents, I think, about the normal asteroid diameter. Can you fit a single asteroid body between those two things, which is anywhere vaguely compatible with the known diameter of the asteroid? So, almost certainly an asteroid. The light drops to the right depth. The physical separation was a key issue there. Now, this is an interesting one. There's the plot of the event with a little satellite there, observed by one observer there, Jan Manek. He used to be heavily involved with lunar occultations and the early stages of asteroidal. It was a 2 data point light drop. If those two missed chords were not present, and if you couldn't measure the light curve drops properly, you could take that ellipse and fit it to those 2 points with the asteroid being up there. So without those two misobservations, that was open to be a double star event which you'd have to exclude just by the light curve drops. But because of those two missed chords there, stop the second body from being up there, and those ones there stop you from fitting it down here. But missed chords can be quite important. How am I going to time? Oh, well, 1 minute. All right, here's one. There's the thing. Light drops too deep for a double star. That's the fit to a shape model, about the right scale. Looks through on this one, clearly well separated. The challenge was this one. This was in the early days of asteroid, and he had serious problems with writing to the USB port. And there's about 70% of the frames dropped over the duration of the event. So that compromised the timing stuff for that the time accuracy for that. This one, 2 chords. This one was using a GPS flasher, and some of people started raising concerns about the accuracy at the time, and that got excluded from the analysis. That one's straightforward. Single chords there. You couldn't put that on the other side of there because of those 2 chords, which helped exclude an elongate asteroid, and it was well defined by 2 chords. I'll skip through a couple of these, given a short time. Yeah, single chord there, and yeah, subsequent observation there. Now this is an interesting one. There's the 2 light curves. Oops, oh bugger, pardon me. Need to get back to this. 2 light curves, main drop and this drop afterwards. Significantly greater than the noise, so hopefully real. But what is it? Turns out those 2 drops coincide very nicely. And when you take the diameter that you fit to those chords and do Fresnel diffraction on it, you finish up with drops that deep. This one, this came through with the processing of the light curve. When I saw that, I said, oh, that's just been processed as a single event, believe it or not. And looked at it and then started asking questions. Turned out it's a binary asteroid. Light curves are important for all sorts of reasons.
Just saying that to make it all happening, yeah.
Oh, yeah.
It's part of that.
This one, there was an awful lot of grief over this one. The journal was one that sort of pushes the boundaries, and to find comparison star that was reliably pleasant. They finished up justifying it on the basis of if you integrate X number of frames, then you can find these stars. And that's sort of limiting magnitude, ignoring the question of what would happen with the actual light drop. And that was a lot of grief. Oh no, sorry, that's you. This is another one I'm talking about.
Well, you don't remember the pain.
Yeah, no, this is straightforward. The other one, there was an American one, and I'm very unhappy with it, but he got somebody else a month later, or a couple of weeks later, got some rotation light curve measurements, and from that, it was clear it was a satellite. The light curve, that stuff, no. This one Steve had, congratulations to Steve. Here, notice the light drops are different. No double star suggestion of that, although the drops are quite deep. Fairly noisy light curve, but when you do the mathematics, that difference in drop is tied up with Fresnel diffraction. Here's another one in Spain. It's a Fresnel diffraction coming into play there, and the light drops exclude the double star. Now, this is one which has turned out to be really complex. Single light curve there, and that light curve with that nice rise in the bottom there. Interestingly, the difference in the bottom of the level at the bottom of those 2 drops. That's a Fresnel diffraction issue, slightly reduced light level. We still haven't quite figured this out, but from those 2 light curves, taking back from there to there, and from there to there, you have those 4 points there, and you can draw a family of ellipses through those 4 points oriented that way, and a family of ellipses oriented that way. That family of ellipses has a maximum diameter of 14K. This family has a minimum diameter of 14K. It goes up to infinite. The narrow-wise diameter is 16K. Which one is right? If this is the right orientation, then it's definitely a satellite. Only question is whether it's a separate satellite or a contact binary. This one, depending on how you configure things, this body could be down here, satellite, or it could be up there a bit, and the graze explanation floats around. And trying to figure all this out, the moment I think that's the most likely configuration of that, and that this should be rounder than it is based on the bottom of this light curve. We've been working on this for some time. I've had Bob Anderson with his Fresnel diffraction stuff, trying to advise on this, and I think this is the last one. Yeah, this one is taking a bit of working on. It's being written up at the moment. 4 chords. There's that chord is this one. Oh, those chords match these chords here somehow or other. Small asteroid. It's that one, I think. It corresponds to that chord there.
The second light curve. The second light curve is chord number 4.
Oh, so that which is the bottom one.
Yes. And the third light curve is chord number 2.
So that's the satellite, and that's the graze one.
That's the graze, yeah.
Now, the challenge with this one is that's the diameter of the star. That's the diameter of the star, and that was a mischord there, and that is likely to be mischord there. And the star was sort of similar diameter, what you fit there. So we're doing modelling of the size of the star against the size of the bodies to try to figure that out. And you're wanting to press the stop button, and
You already have.
and here we've got an issue that the ellipse can be oriented either that way or that way. And it looks like I can use the modelling of the star diameter to decide the orientation of this ellipse using that graze chord. And that makes relevance. If it's oriented that way, that makes more sense than if the asteroid is oriented that way. And I think that's it. I hope that gives an indication of the complexities that can arise with satellites. It's not straightforward. Sometimes it can be, and other times it takes weeks or months to work through it all.
That's right.
So questions for Dave? While I open the next file, can you, opportunity for questions?
Any questions? Have I stunned you all?
Must take a lot of time to work out all the different possibilities.
And you've got to exclude everything else. When I get involved in these satellite things, some people get really pissed off.
Yeah, they think you're an obstinate bugger standing in their way.
Exactly.
Yeah.
And he is.
I've seen some of those comments, yeah.
Yeah, and our reputation for discovering satellites really depends on us being rigorous at this stage of the process.
Yeah.
Yeah, we're not having egg on.
Reputation from the past.
Yeah, we've got the lousy reputation we had from the 80s and early 90s There's a real value.
Yeah.
Okay.